algorithm for numerical integration, brought to you by Moscow's top FM station, WKGB, and we know where you are. I dedicate to Monty, who of course did the 41CL gem. It's more than awesome, so he deserves our thanks. The background is, we all know the Simpson's basic rule. In fact, it was implemented in the math pack of the 65, 67, and so on. Very simple. You integrate between A and B, a function, and you take 3 readings at each end and in the middle. And of course, if you make, you can, if A and B are close enough, you're good enough. If so, you can chop the interval into subintervals and apply Simpson's method. And you can either use the chaining formula, where it becomes F1 and then 4 times then 2 and 4 and 2 and alternate. Or you can just apply the basic formula independently on each subinterval, and you can even change the subinterval length if the function is not doing a lot of variation, to save some time. So one night I said, what if instead of I pick a value m inside the interval a and b such that f of m is the average of the function values at a and b. So, which of course the question is, but where is m? And to derive a formula to calculate m, of course I first get the midpoint c in the interval. I calculate f of c, so I have a, b, and c with the function values. I have 3 points, a quadratic, and I do an inverse interpolation to calculate m, where, again, formula 3 tells me what f of m is. And that's a little bit kludgy here. And I want to get the formula p of x, a quadratic, based on f of a, f of b, and f of m, and their coordinates. So this is what I get with the equation 5. On the way to clarifying things, I define CA, CM, and CB, and then the constants K1, K2, and K3, which I then plug in to find my quadratic polynomial. Now, if I do just straightforward integration, I get the equation 5 with a constant term that pops in. But we are doing integration over an interval, so over a and b, I have equation number 10. And it seems to be a little bit complicated. More crunching CPU time is needed. Now remember, Simpson's rule was in the days where the legacy algorithms where they kept things simple because they had people doing the calculations and then maybe somebody else verifying. If they did something like that, the possibility of errors and even the error checking would be more complicated. Yeah. But we use equation 10. Again, either if a and b are small, close to each other, that's fine. If not, we chop it into, and we apply the formula into the subintervals, and then the beauty of integration, you just add the subintervals and you're fine. In this case, I use the Excel VBA to implement the half function value quadratic integral. That's what I'm calling the algorithm. So I did a test. I said, okay, let me pick my favorite function, f of x equals 1 of x. The integral is the natural log, very easy. And I created a set of tables. This is the first one. They're all similar. I'm integrating just from between 1 to 5 and using n number of divisions as 5. So the second column shows what the new algorithm does. It gives me 1.60 and actual integrals, kind of close. And then Simpson's is a little bit more off. Now, I asked myself, if I increase the number of intervals with Simpson, how high must I go to match the new algorithm. And in this case, it's 88. And I went, that's interesting. Well, let me do this, generate another table going, changing, everything stays the same except n goes from 5 to 10. Again, now Simpson's at 10 intervals gives me less error than before, but if I wanted to match the new interval, I have to set n to 1300. Whoa, okay. Well, and when I go to 15 intervals, I have to go back to up to 6,500 sub-intervals so that Simpsons could match the new algorithm. 20, it jumps to 20,000 versus 20. And then 25, the new algorithm versus 50,000 segments with the Simpson. 30, it becomes 102,000. So you know where this is going. It's an exponential. And again, 35, it's almost 200,000. Here's a table that summarizes what I did, comparing 5, 10 in increments of 5 here. But look what's happening with Simpson if I wanted to match the accuracy of the new algorithm. And here's a little, it shows, it's not a perfect exponential, there's some deviation, but certainly it shows an exponential trend relationship between how many intervals Simpsons needs to match the half function value algorithm. I also did experiments with different functions, the exponential, square root, cube, and even hyperbolic sine. I picked arbitrary integrals, and I used n10 here, and you can see for Simpson is, for some function it does better than others, but still, the matching number of intervals to achieve the same accuracy, or thereabout, is very high.
How did you determine that number? You actually...
just try it, you know.
Really?
But, yeah, it's like you eyeball it, like, okay, it's eyeballing it.
So, Namir, you're talking about matching the precision of the new formula, but we've all done Simpson integration. You don't need 1 million intervals to come close to the actual number. So, the accuracy of the new formula to the actual number is also part of that question, right?
Okay, the new algorithm doesn't need so many divisions to achieve accuracy.
I understand, but you're comparing how many iterations or
Yeah.
how many intervals of the classic Simpson to get the same accuracy
As the new
of
interval.
one. Right, but my question is, we've all done Simpson, you don't need 1 million intervals to get really accurate numbers.
No, the thing is, 1/x is actually one of those tough.
A hand-selected case?
It's a tough, yeah,
Okay.
yeah. It's a good one for testing in numerical. So the new algorithm requires certainly more calculations per subinterval than Simpson, definitely. But it yields phenomenally more accurate results than Simpson's rule. Now, just after I finished all that, I was on vacation, North Carolina beach, very nice weather, and I said, what if instead of just half, if I go 1/3 of the way in the interval as far as function values, and this way I would go from a quadratic formula to a cubic formula. Of course, it got exponentially more complicated. The thing is, unfortunately, it bombed out because I had to compare it with Simpson's 3/8 rule, so that I'm comparing apples with apples. I have the same number of points. Unfortunately, it didn't give anything. In fact, Simpson's 3/8 rule was always slightly better. So going to the cubic does not pay off. The half function value algorithm is better, and we kind of leave it at that. Otherwise, it's better to use Simpson's 3/8 rule, which really, if you've tried some integrations, doesn't give you really better stuff. The basic Simpson rule is better. And today with our fast machines, if you increase n, you can get really good results, even with the trapezoidal rule stuff. And that's it, so we're good time-wise?
Hey, Amir,
Yes.
so in terms of computational efficiency, regardless of number of segments and so forth,
Mhm.
is Simpson's rule still the best if you just increase the number of segments?
Yeah.
The computational required for the quadratic?
Surprisingly, in general, yeah. I used to think, use Gaussian quadrature and all that stuff, but with today's machine, the speed has looked favorably on Simpson's rule, because the code is simple, especially for a calculator. The code is simple, and if you don't mind to let it crank a few more iterations, you're good. You know, the other Gaussian and all becomes complicated to code. Yes.
Just a comment, when you do Simpson's rule or Simpson's 3/8 rule, that's a case of what's called Newton-Cotes integration.
Yes.
And what you are actually finding is not the integral of your desired function, but the integral of a polynomial that matches your desired function at those specific points.
Yes. Simpson is
And
based
the
on a
higher the
quadratic.
degree of the polynomial, the better the fit.
Yes, Simpson is based on a quadratic approximation also. But it's using the mid-interval. I'm going like, no, I want to see where the function value is middle. And when you have, when the intervals or subintervals are small, then you're not afraid of the function zigzagging in, between A and B. It's pretty much smooth. Any other question? We're good? All right, lunch.
Thank you.